Welcome back to the Ephemeris Podcast. I'm your host, Feeling, and it is nice to be back for another episode in Season 2 where we continue to talk about cosmology from the past and leading into the present. So, yeah, last week's episode caught quite a lot of views. I think at the time of recording it has surpassed 100, so I'm really proud about that. And yeah, the shorts have been alright, but that's no biggie as long as the episodes do well. So yeah, let's get into today's topic. This week's saga will be on the man, the myth, the legend Hipparchus. And funnily enough, I'm not only saying that for the intro. I don't say that lightly because we are going to find out why Hipparchus might actually be the man, the myth, the legend in today's episode. So let's get on with it. As the trend goes with a lot of Greek astronomers, little is known about Hipparchus other than the fact that he was born in Bithynia in modern day northern Turkey, and that a lot of the work that he did has not survived. I believe it is one out of the 14 he is known to have written. So his promising work, however, had to do with lunar and solar cycles as well as the precession of the equinoxes. So let's start with lunar cycles. He proved accurate results for the period of two different types of lunar cycles. There's one very commonly known, this is the synodic month, and then there's the anomalistic month. And so the story goes that Chaldean astronomers had already come up with a value for the period of the period of lunar cycles in general, and it's basically summed up in the value of 251 synodic months being equal to 269 anomalistic months. And I'm not going to get too specific into that fact. I'm just going to throw that out there because we're a little bit more concerned about what Hipparchus did with this value. So what he did with it is he said, look, if I multiply this value by 17, I will get an interval in time in which the moon will have identical latitudinal positions. So kind of the way you'd imagine that in 365 days, the Earth is going to be in a similar place in the solar system and a certain distance away from the sun. So basically, Hipparchus did almost a similar thing where he's like, okay, if I take this value of the lunar cycles from the Chaldeans and I blow it up by a factor of 17, I'm going to get a period of time in which the moon reaches identical latitudinal positions. And really the only good way to prove that this premise was correct would be to see if there were eclipses that were spaced out by that time frame, or which is kind of the value of time that Hipparchus blew up. And I think that value was about 345 years. So yeah, he used Babylonian records to confirm that an eclipse observed by the Babylonians and the eclipse circa 140 BCE was indeed 345 years apart. So that confirms the fact that the moon would be in identical latitudinal positions in that the time frame that we have just discussed. And what's even cooler is the fact that the method in which Hipparchus multiplied it made the calculation of the synodic month even more accurate, which is kind of weird. Like, I couldn't tell you of any other time in which sizing a number up actually reduced the error of a calculation. So yeah, that really messes with my head, that one. Another amazing mathematical thing that Hipparchus did was this. Earlier astronomers noticed a change in speed of the moon, and they had two theories as to why this was. They said either the Earth was not at the perfect center of the moon's orbit, because obviously we're in the time, kind of the period of time in which people believed in a geocentric model, as you'll know from some of the previous episodes. And so that was one reason that Earth was not at the perfect center of the moon's orbit. Or there's another theory that goes that the moon had an epicycle, which we have talked about. I believe it was in the episode of either Anaxagoras or it was Anaximander. But yes, we have talked about epicycles, so go check out some of the earlier ones to get informed on epicycles. Hipparchus, basically, he took these two theories of either the Earth not being at the perfect center or the moon having an epicycle, and he used math to say these two things are literally the same thing. So for the eccentric model, which is the Earth not being at the perfect center of the moon's orbit, the statement goes that Hipparchus found for the ratio between the radius of the S-center and the distance between the center of the S-center and the center of the ecliptic. So basically how I would dissect that statement is Hipparchus took the value of the difference between the Earth center and the actual center of the moon's orbit, and he compared it to the radius between the Earth center of the orbit and the kind of the edge of the moon's orbit, and he compared those two values. So for the epicycle model, he found for the ratio between the radius of the different and the epicycle. So that's that one's a little bit difficult to dissect more so than the eccentric model, but those are the two kind of statements that popped up on the article that would sum up how Hipparchus found this mathematical equivalence. And in fact, Hipparchus is the first astronomer known to attempt to determine the relative proportions and actual sizes of these orbits as well. And I believe I mentioned with Plato a statement in which he said, like, one celestial body's orbit is sort of it has a proportional relationship to the orbit of other celestial bodies, but here he really puts the numbers to it, so that's definitely a new thing. So that's lunar stuff. Let's look at some solar things. Hipparchus knew the accepted value of the tropical year at the time was 365 and a quarter days. However, he noticed an error in the timing of the equinox and an equatorial ring's indication of the equinox. So equatorial ring is kind of an astrometrical instrument that was available at the time. So he noticed an error between when the equinox actually happened and when this instrument predicted it would happen. And he concluded that the error he noticed would equate to 1 day difference between the prediction and the actual equinox every 300 years. So he subtracted this value from the accepted value, and this made him only 6 minutes off of the accepted value today. And we've talked a lot about precision with some of these astronomers, and that's just another great example. Jesus wasn't even born in his time, but yet he was still doing God's work. I thought of that statement, saying that statement for the clip. It's a little bit cringe, but you know what? We're gonna settle with it. As for the orbit of the sun, Hipparchus assumed that the Earth was not at the center of the sun's orbit because the difference of the length of seasons was evident to him. So, he assumed that Earth was not at the center of the sun's orbit. And before I get into astronomical instruments, I will mention that Hipparchus had an extensive method of calculating parallax, but sort of the method in which he did it with the resources that he had, it's a very, very difficult method to analyze. It's easier, obviously, to understand parallax in modern terms, which is something I've tried to do, but with the way that he did it, it's even more confusing to me. So again, I would not do his methods justice, so I will not fully discuss that. But just know that he did it. It's fairly important. So in terms of Hipparchus's astrometry, this anecdote I found kind of sums it up perfectly. Hipparchus is credited with the invention or improvement of several astronomical instruments which were used for a long time for naked eye observations. According to Synesius, he made the first astrolabion. This may have been an armillary sphere, which is, again, a tool that they used to use during the time, and perhaps Hipparchus was involved in a more sophisticated version of it, or a predecessor of the planar instrument called an astrolabe. And we've talked about astrolabes with Persian astronomy, so no need to get too deep into that. So with an astrolabe, Hipparchus was the first to be able to measure the geographical latitude and time by observing fixed stars, which is interesting because we I think with a lot of earlier observations, you wanted to associate a time with kind of the set and rise of stars, but what if you could do that in reverse, which is a little bit of what Hipparchus may have tried to do. Previously, this was done at daytime by measuring the shadow cast by a gnomon, which is, I guess, it's sort of a sundial. By recording the length of the longest day of the year, or with a portable instrument known as a scaphe. Another great quote that I found: Hipparchus applied his knowledge of spherical angles to the problem of denoting locations on the Earth's surface. Before him, a grid system had been used by okay, I do not know how to say the name of the guy who figured it out before with the grids, but some dude did. But Hipparchus was the first to apply mathematical rigor to the determination of the latitude and longitude of places on Earth. And that's a little bit more geographical, but it definitely has to do with some of the instruments that he was using. So perhaps loosely related to astrometry. So yeah, that is a lot of the achievements that Hipparchus made, and for this reason a lot of people actually call him one of the greatest astronomers of the Antiquity age. And the Antiquity age is kind of what we've been covering with some of the 4th century BCE Greek astronomers, and a little bit earlier than that with Anaximander and Anaxagoras. So yeah, once we get out of Antiquity, obviously, we'll be getting closer to the Middle Ages in terms of astronomy. But yeah, that is all I have for Hipparchus, is basically what I'm trying to say with that. And hopefully you guys enjoyed the episode. If you guys did, and you're listening on Spotify, thank you very much for listening on Spotify. And I would sincerely appreciate a follow there. If you're listening on YouTube, to some 100 people, hopefully I'm speaking to with this podcast episode, I would sincerely appreciate a subscribe, just to know that you guys are here to stick around and show some support for the podcast episodes. And until next week's episode, I will see you guys later. Peace.